Hi everyone, I'm Philipp. Let's see where we can take this. So, who is using databases? That's, yeah, most of you. Good. Who is using search already? That's far fewer. Well, let's see why and what even are the differences between databases and search, or what is the general idea? So I always try to explain it with this picture. And one side, that one here, that is kind of the database. It's very black and white. It's you store something and then you want to retrieve whatever you've stored directly there. And you want to just are looking for direct hits and you want to retrieve those. Whereas search is the other side, this scales of gray, like where you are more interested in the general concept. It's not about black and white, this is an exact match or this is not an exact match. This is more like you're searching for some concept or something that you're interested in. For example, when you type some search query into Google, you're not interested in just exactly the thing you have typed in, but more like maybe something similar or maybe something slightly spelled differently. So it's not just this black and white, but it's more about concepts and searching for the overall topic or thing that you're interested in. And you can do that with Elasticsearch, which we provide. It's open source, you can just use it, you can see how it works. And I want to quickly explain today how it actually works and what it's doing and why it's so different than what you do with a database. So if you're searching on any of these sites, GitHub, Stack Overflow, Wikipedia, behind the search box, there's always Elasticsearch doing the search for you. You don't see the actual queries, but behind it is Elasticsearch doing those queries for you and giving you back the right results. So, like I've been introduced already, I work for Elastic. My title is like developer advocate, so I mostly get to play around with stuff and build demos and show how stuff works. That's the general idea of my job, just to explain what is what and how does it play together. If you have any questions and you don't want to ask in the middle, I'm using Slido, so you can just go to Slido and then my Twitter handle and post any question there. And at the end, we'll have probably time. I'll look at those questions and I'll answer them. If we run out of time, I will just tweet out the answers. But I think we have an hour, so we will probably have enough time to actually answer everything that we need. Cool. So if you want to ask any questions, this is the one thing to remember. Post your questions there. Otherwise, I guess we can jump right into the details. So one of the main differences between a database and a search engine is that you do more work up front. So you basically prepare the data the right way so that you can efficiently search it afterwards. That's the overall idea. So what you have is Apache Lucene, which is like the core library, which is just writing it down to disk and doing the actual search. And Elasticsearch around it is like the thing you interact with, or the shell. So the shell as in the seashell, that's kind of like the outer living thing. So you interact with Elasticsearch. It provides a REST API to run queries. It provides the query DSL. It does the distribution of the data. It will take care of all of that. And then Lucene is actually writing it down to disk and running the actual search queries. Sometimes people ask, like, what is the database behind all of this? There is no more database. Like, Lucene is already the thing writing to disk, so you don't need any other database or data store technology behind that. That's all you really need. Okay, so let's take a practical example. I'm not sure if you have the movie dubbed in Polish, but who knows what the phrase is in Star Wars when he makes that hand movement in English? Yes, these are not the droids you're looking for. And we want to look at this one sentence to see what search does when you store something. So let's assume we have, these are not the droids you're looking for. We have this emphasis tag from HTML around the not, because that's emphasized. What is actually happening behind the scenes when you store that? So the first thing you normally do is you throw out any formatting. So the emphasis tag, nobody is going to search for this emphasis tag. We assume it's just formatting to read it or for the visual part. But for searching, we don't really need that. So we'll just strip out any formatting. If you have HTML, we have a function called HTML strip, which will just kick out any HTML that you have in there. Easy. The next step you think that you do is you tokenize. Tokenizing is, at least in Western languages, pretty much like you break up the words. So you can see the dot at the end is gone. all the punctuation marks are being removed, and I have added some more space between the words because we've basically broken up all the words. In other languages, like in Asian languages, in Chinese or Japanese, this is much trickier. But since I don't really know how they work, we'll ignore them for today. And we'll stick to Western languages. So basically, white spaces and punctuation marks, those are the ones where you break up your stuff, and then you just work with these tokens that you have extracted. Next, what you do is we are lowercasing everything. The only change we had here was the D's was lowercase. Everything else stayed the same. Why are we doing that? Because, well, it's a different ASCII or UTF-8 character in the background. So you don't want to search for both of them. You just lowercase everything, and then you just have to search for the lowercase version. Because most of you are probably not properly uppercasing and lowercasing when you search on Google. Just to avoid any unnecessary work around that, we'll just lowercase everything and store that. There are some specific scenarios where you might not want to do that. For example, sometimes upper and lowercase might make a difference. So if you have US, the United States, or us in lowercase, those might be different concepts, and you might want to use them to make a differentiation between them. But generally, we don't really care about upper and lowercasing, so we'll just kick out any uppercases and lowercase everything. Then we remove the so-called stop words. And you can see now my sentence is much shorter because these are not the droids you are looking for. Cool. Okay. Let's continue with that one. So what you do is you remove the stop words. The idea behind stop words is these are words that are in almost every sentence or text that you have. And they add very little meaning because even if you would search for them, you would find almost every possible text because these are not. They're just very common. They're all over your text. So if you search for them, you wouldn't find anything relevant. You would just make your search index much larger, and you don't really gain much. So you don't always have to do that, but in many cases it makes sense to remove those so-called stop words. And then we can stem the words. So what stemming basically does is it reduces a word down to the word root. And as you can see, English is a very simple language in that regard. So we had the plural for droids, and you probably don't care if something is droid or droids, you just care about the concept droid. So we simply cut off the S to make it a singular, to just reduce it down to the word root. You sometimes might not even care about if something is a noun or an adjective. For example, you could search for beautiful and beauty, and they would be stemmed down to the same word root because it's kind of the same concept that you could search for. There are different stemmers depending on what languages you have and how aggressive you want them to be. One that is very common for English, for example, is the so-called snowball stemmer, which has some built-in rules. And something important to remember there is this is not based on dictionaries, so this doesn't really understand anything. This is just based on rules. So the rule would be, for example, to cut off the ing at the end of the word for having, or whatever the word is. It cuts off the s at the end because it is normally the plural, or maybe it's the third person singular where you add the s. So that's just stuff that doesn't really add much value. It's just making words different, which you don't want. So you just cut it off and stick to the word root. That's the general idea. So to try all of this out, you could, the two easiest options are, we have a free trial for our cloud service, so you can just use our cloud service and spin that up and run it there. Or since everything has to be Docker nowadays, obviously you can run this in Docker as well. The minimal example would be something like this, where you have, I'm using Elasticsearch to store the actual data, and then for the interaction, I'm using Kibana to make my queries slightly easier to run against this. You will see why and how in a moment. So you could just run that. Let's see how stuff is actually being stored. Or let's not actually store it yet. Let's simulate how it would look like if we would store something. So we have a so-called analyze endpoint. Basically, you can throw a text against that, and it would show you what would happen if Elasticsearch would store that to disk. It's not doing that actually right now, it's just showing you what would happen. So let's take our English sentence. These are not the droids you're looking for, and actually we can try that out live. So here, this is Kibana. If you've never seen Kibana, the thing here is to, for example, get the current version is we just run a get, and this would be the equivalent to this curl command. No, it already shortens then that down here. We'll need the command line to actually show that properly. So for example, this would be the equivalent, but rather than typing curl x get and then the server name, the port, I just type the get and the part where I'm actually adding the meaning. So it's just a bit simpler, especially if you have document bodies and everything. That's why I'll stick to Kibana to run these queries. But it's the same thing that curl would be doing. So when I take my text, so these are not the droids you're looking for. This is the sentence that we had in the beginning. And I just run that against analyze. And when I run that, what you are getting back is you get these extracted tokens out of that. So you can see droid you look. Those are the tokens that have been extracted. And you have some additional information around that. You have a position. Do we start counting at 0 or 1? These are not the droids at 0. Like every proper system, we start counting at 0. And then you can see the first tokens were removed, and the fifth, which has position 4, is droid. Why are we extracting that position? What could that position be important for later on? For example, if I search for a phrase. It's a weird phrase, but let's assume somebody searches for droid you. Which would be exactly what we have in there. What we could then very easily do is, we wouldn't have to look at the original sentence anymore, we would just look like, which documents have droid and you, and which have the position where one is followed right by the other one. And that way, once you have extracted that, you can very easily and quickly do a phrase search for that. The other thing that we are extracting here is the start offset and the end offset. Why might this be important? For what could that offset? Sorry? Highlighting. Yes, exactly, highlighting. Because otherwise, so highlighting, when you want to show it, especially in a long text, where is my hit, you need to set a marker, for example, an HTML tag, whatever. If you don't extract those positions, you would then need to reread the potentially long text and then find where is my actual token and then highlight that there. If you just extract that once, you can use that very efficiently afterwards to highlight those hits. You could also define this entire pipeline that we've talked about before, like this here. Here you can see we define the HTML strip. We use the standard tokenizer. You could also use a different tokenizer for some specific scenarios. For example, this might break up URLs or email addresses in the wrong way, and you might want to customize that. Then you can see we lowercase everything. We remove the stop words. We use snowball stemming, and then we have our sentence, this time with the HTML tag. What is the output, or what should the output be of this one now? Exactly the same as before, hopefully. So when you run that, you can see droid you look, it's doing exactly the same thing. But you could, for example, say, I don't need HTML strip because, for my example, there is no HTML. One thing that you can already see here is that search is normally rather dumb. It doesn't really understand your sentence. So here, for example, you can see these are not the droids you're looking for, but the not is actually a stop word. If you had something like natural language processing, the not would make a major difference because you're interested in, are there droids or are there no droids? But what full text search does is, it doesn't really understand your sentence, it's just working on these tokens. So you extract the tokens and then search for similar tokens. It's dumb, but it is very fast. That's the big advantage, and it will scale very well. Whereas natural language processing, it's much heavier and or more error prone. But we don't understand the sentence here that is happening. So we've done some of those. Sometimes people ask, like, how many stop words are there? It's pretty well hidden in the Lucene source code, but it's like 33 or 35, I always forget. It's only a couple of stop words. It was just a pure coincidence that in our first sentence that we had so many stop words. But you can see these are all the stop words that we have predefined in English. That is, of course, language dependent. And you could add your own stop words if you say, like, for my specific use case, a different set of stop words might make more sense. Should you always use stop words? Who says yes? Who says no? Where are the consultants? They always say it depends, right? And then they charge a lot of money. Obviously, it depends, because in many scenarios, it's okay. But in some scenarios, it doesn't help you so much. For example, here, if you have Shakespeare's to be or not to be, those are all stop words. If you use stop words, you would never be able to find that again because it's gone. So you will need to either combine stuff in the right, or like you could search multiple ways, or maybe for some scenarios, stop words are not the thing that you want. You'd need to pick the right one. These are all the languages that we support by default. What are we missing? Yes, that is kind of unfortunate now, right? So languages are always language dependent. For example, in English we have this is, has, possessive, the s that we just throw out. In French we would have, for example, the article in the beginning, so we would cut that off, or the accent. In German we have these weird umlauts and that special s thing. In German they don't make any difference, so we just throw them out. And reduce them to the ASCII characters. In other languages, they do make a difference. For example, I think Swedish also has an A umlaut with the 2 dots, but there it's a totally different letter, and they keep that. But that's something the linguists define, whatever makes sense for your language. Okay, so what are we going to do about Polish? There are plugins to add more languages. For example, the Asian languages are very complex. Also, Polish is unfortunately a complex language. And for those, we have plugins that you can add. Why didn't we put that into the core? Because it would make the download much larger, and you would always need to load something into memory, so the memory footprint of Elasticsearch would also be larger. So for those use cases where you need those languages, you will need to install those plugins to actually work properly with those languages. The one for Polish is called Stempel. I have installed it in my demo, so we can actually use that. And then those are the official ones provided by us. There are also some by the community. For example, Hebrew, under a very specific license, is available from a community member, and other languages like that. So, I think this is kind of similar, right? More or less. Okay. What happens if I throw that through the same pipeline, but with Polish? What will remain? Any guesses? Which words might be remaining? Most of them. No, I have bad news for you then. So if I run that, this is what Stempel, the Polish analyzer, keeps. Does this mean something like look? Okay. Yeah. So here you just have draw it and look. Those are the only ones that remain. What would happen if I used the English analyzer on a Polish text?
I thought that was the question you asked before. I mean, not the Polish analyzer, but English analyzer.
Yes.
Only remove two, right?
Yes, it will remove the 2. And like the rules just don't match. So that the 2, I guess that means something different than 2 in English and Polish. 2 are different words, so it's just removing a totally different word by accident. And then the stemming rules also don't apply. So that doesn't make much sense. So what you need to do is you need to know what language a text is in before you can actually properly analyze it. Otherwise, it will not do the right thing. You can detect that. We have a so-called ingest pipeline. You can add that. It's another plugin. Basically, I create this pipeline and then say there is a field I call quote, and I want to add a language field afterwards to the text that contains that language. So when I store that pipeline, I can then run my document and say, this is the quote I want to analyze. And when you run this, next to your quote, you will always also have the language. And luckily, it detects that this is a Polish text. it works reasonably well to detect the language of text, especially if they're longer. Like if you only have 1 or 2 words, it might be tricky to get the language right. But this one can detect the right language. And then in the next step, you could take this and store it as Polish text with the right analyzer. And then the rules would match. Okay, so we have extracted those. If you want to find out where the Polish stop words live, it's also pretty well hidden in the source code, but this is where they are. I'll publish the slides afterwards so you can look them up. I've checked, I think it's 180 words approximately, which are in the Polish stop word list. So much more than in English, but other languages have even more. So it's just a bit dependent on what linguists figured out, what are the common words that don't make much sense to keep. And in my example, these are not the droids you're looking for in Polish, because I cannot pronounce that. There were also many stop words in that. So we worked that out. Okay, let's look at another example, or actually let's do that live. So we're using the same pipeline as before, and I'm using Obi-Wan never told you what happened to your father. What will remain here? Or let's start off like Obi-Wan will be 1 or 2 tokens afterwards. Yeah, that depends. You just need to know what the tokenizer is doing. The standard tokenizer is breaking it up. So you can see Obi-Wan never told you what happened your father. So in this example, we have very few stop words. It's almost the original sentence. There's only 1, 2 that is being removed. But this is just pure coincidence because we had these stop words in there or not. And we can just use them. Let's assume we have this one here. No, I am your father. What remains when I run that through the analyzer? Yeah, it actually slightly more. It has I am your father. Only the no is the stop word. Everything else is not a stop word, so we would store that. Okay, so far we've only simulated what would happen if we would store something. But now let's actually store something so we can actually run queries against that. So you probably know the schema in a relational database. Elasticsearch has something very similar in the background. We just call it a mapping, but it's doing the same thing. And this is where you define a lot of stuff. So for example, what we're defining here is, I'm defining synonyms. So I have father and dad, and I assume father and dad are the same thing. So if I have father in some point and I search for dad, I want to find the exact same position. You can also do a replacement. For example, here I replace droid by droid and machine. And the effect that has is that every droid is a machine, but not every machine is a droid. Make sense? Because there are machines that are not droids. So basically droid gets expanded to droid and machine, but machine wouldn't expand to droid because we have it one way that we replace that. I put this configuration into my synonym filter. Then you have this analysis pipeline that we've seen before, and as the very last step, I add the my synonym filter. I put this into, I just call this my analyzer, and then I say I have this mapping here where I have the field quote, it's text, and uses my analyzer. So this is how I tie these together. Now I'm storing, this is my pipeline to analyze the text, and then I can actually store documents. So let's create that mapping. You could actually check the mapping, and the mapping would show you, yes, there is one property called quote, and that uses the my analyzer. You could see in the settings of that index, which is more or less what a table would be in a relational database, but it's not a very exact comparison. So its index just contains related documents, and they're sharing these analyzers and fields. Here you would, for example, see we have Star Wars, and Star Wars has this analysis pipeline that we've just configured. Okay, so the first thing we want to do is let's throw the 3 documents that we had before. Let's store those. And I'm just running that, and I've stored them. So if I retrieve my first document now, you see we have some metadata around that. We have the index name Star Wars. We have an ID of that document. Since I have the first version, every time you update that document, it would be incremented, the version. And then we have the source, which actually has, these are not the droids you are looking for. To use that like a database where you just want to have the actual document, you could add _source just to retrieve that, and this would give you back exactly like a database what you have stored in there. But that's not really the point. The point of a search index is to actually do proper searches. We'll get to that in a moment. There's just one more thing we should cover before diving into that. The actual data store that we have in the background here is a so-called inverted index. So what we do is, these are all the tokens here on the left-hand side. These are all the tokens that we have extracted from our texts. They are alphabetically sorted, and they have a pointer basically and say this token here, M, appears not in this document, but in the third document it appears one time at the position 2. And then you see droid appears once at position 4, etc. So for every word, we basically have a pointer to the document. And for your search, then, that one is very efficient because basically you're searching for something, you're extracting those tokens. You look up in the list where are the tokens, and they point directly to the documents where your hits are. And you know how many times they're appearing and at what positions. So you could also do a phrase search very efficiently. And that's why search is very efficient afterwards. Whereas if you do, for example, a like search in a relational database, it would be very slow because it needs to touch or go through all the entries that you have to find something. Okay, let's run some more queries and do something. What would be the SQL equivalent of this query here? Star Wars, yes, exactly. Select asterisks from Star Wars. We don't have any condition, we just have a match all. So this should retrieve 3 documents, and it tells you here we have 3 documents in total, and these are my 3 documents that I have retrieved. But that's not kind of the fun part. Let's do an actual search. So here we are searching for droid. How many documents will I find when I search for droid? Yeah. You see we have 1 document, and these are not the droids you're looking for. What would happen if I would say I'm searching for droids? Would I still find something? Yes? No. Yes, exactly. That is a very important point. Your search terms that you have here run through the same pipeline for all your stored documents so that you have a direct match. Because we do the same stop word removal and stemming, we can look for exact matches afterwards. What downside do you have to this approach though? That once you have defined this pipeline, you can never change it at runtime anymore, because then your search queries would not match the old documents that you have stored. That is kind of the downside. Once you have extracted something in one specific way and analyzed it and stored it, your search queries will need to run through exactly the same pipeline that you can have these exact matches. Otherwise, it will not work. What happens if I search for dad? How many documents will you find? Yeah, I think it was 2 as well. And here the synonyms are at work. So you see, no, I am your father. And Obi-Wan never told you what happened to your father. It's dad, but because we have defined the synonym, you're just finding the same thing. And it doesn't make any difference if you have dad or father. They're really exactly the same thing. You can also have explained why something matches or doesn't match. So for example, here, if you say, I want to know why my document 0 did match or did not match. And you could run this. So if you run this, it says like, nope, this didn't match, false. If I run it for 1, should that match then? Yeah, this one was a trick. Why? Because I indexed my documents 1, 2, 3. So the result for 0, this document doesn't exist. So this is the result for something that doesn't exist. This is the result for something that doesn't match. And this is the result for something that does match. And then it would tell you why it matches. And then you have this, the score here, the score, the explanation why it matched. We'll get to that in a bit to see why something was matched and how do we rank these documents. Before that, we could search for machine. If I search for machine, Will I find something? Yes. Every droid is a machine, but not every machine is a droid. So that's the way to remember it. You can also do a phrase search where I search for I am your father. And that would only find that one document that really has I am your father. And that will make sure one token is followed by the next one. And all of them need to be there. So all the search terms in your query need to be there. You can also have a slop. A slop is basically you can have one offset in there where something is, where there is another token in there and the positions don't match exactly. But all the tokens from your search query need to be in your result query. So if I run this query for I am not your father, will this match or will this not match? Yes, exactly. The not is a stop word, so this is basically removed. Then we have this one offset in here between the found result and the other one, but it will still match. But what would not work is I am your loving father. Would this work? No, because there we have something in the search query, the loving, that is not in our result, so we would not be able to match that. So here you don't find anything. You can also do something called fuzziness. For example, you forgot how to spell Obi-Wan, and you spelled it as van with a V. And then you can set the fuzziness. And it will find something, it will have a lower score because it's different, but it will find this. What the fuzziness is basically is a Levenstein distance. Most of you remember Levenstein distance from university? More or less. So the Levenstein distance is basically, if you had a Levenstein distance of 1, it's like one edit. It could be one character too much, missing, or different. Depending on the algorithm, like 2 letters exchanged might be an edit of 1 or 2. That depends a bit on the algorithm in Levenstein distance. What the fuzziness of 1 does is exactly the same thing. If you set the fuzziness to auto, it will set a fuzziness value depending how long your search term is. So if you have a search term for up to 2 characters, the auto fuzziness would be 0. 3 to 5 characters would have auto fuzziness of 1, and more than 5 characters would have an auto fuzziness of 2. So you could either set it as an exact value, or you can just let Elasticsearch use the defaults, what we consider a reasonable number of edits, depending on the length of your search term. If you search for Obi-Wan and you misspell both and you have a fuzziness of 1, what will happen? Will you find something or will you not find something? So we do find something, it's the same result. Any guesses why? Yes, the fuzziness is per token, which is something that might be a bit unexpected and something you just need to know, but the fuzziness is on a per token level. So since Obi-Wan is broken up into 2 tokens because of the dash in a standard tokenizer, you have 2 or 1 edit per word that you can use. So this is just something you need to know because it might be a bit unexpected. Okay. Let's head, oh yeah, by the way, this is kind of a fun story. A few years ago, initially the fuzzy search in Elasticsearch was brute force. We would just generate all the possibilities you could do with Levenstein 1 or 2. And search for all of them. But this was not very performant. And there was a very interesting paper that nobody understood to implement that in a better way. And then that's the blog post I've referenced there. Then somebody in their spare time wrote the Python implementation of that. And the developers in Lucene didn't really understand what it was doing, but they were just re-implementing the Python stuff in Java directly to work in Lucene, and it just worked. And nobody really understood why, but it was very easy to test the old against the new implementation, and it was much, much faster than before. And what you have is basically, it's called the Levenstein automaton. Here, for example, we search for food with a Levenstein distance of 2 or 2 edits. And you can see any way, or we start in this at this point here, and we need to find one way to reach the top right corner, so from bottom left to top right. And any way is fine. So for example, you could find food, and then you have basically 2 edits or wildcards left. Or you could have any combination to go through this network. This is the Levenstein automaton that is being generated, and you try to find one way through here, and that's something that then matches. That's the general idea of that. To try to do that in a relational database would look something like this, and that's probably not going to be much fun, especially with longer words. That might be quite some typing. Anyway, so let's get to the score, because so far we've pretty much ignored why something was ranked higher or lower than something else. And that's an important part of full-text search, that we have this so-called ranking or scoring. Like, how relevant is something? And the base idea is behind this. It's called term frequency, inverse document frequency, TF-IDF, if you search for one term. We have slightly tweaked the algorithm, but the same idea still applies, and it's now called BM25. The idea behind BM25 is it stands for best match 25, so it's the 25th iteration of the best match algorithm. So maybe at some point we will have BM28 or whatever, when there are some new iterations to make this algorithm even better. How does it look like? So, the first general idea that you have is the term frequency. It assumes if you search for father, and one document contains father once, and another document contains father 3 times, the document containing father 3 times is more relevant than the other one. I guess that's kind of intuitive. And it looks something like this. So you have the relevancy, or let me point here, the relevancy, and the number of occurrences of this term you're looking for. So here you can see if something appears once, it's less relevant than something that appears 5 times. However, then there is a difference in TF, IDF, and BM25. The newer implementation basically assumes once you've reached 5 occurrences, it doesn't really change much anymore. It doesn't get much more relevant anymore. So we basically cap the growth here pretty strictly. Whereas TF, IDF assumes, well, 10 is still better than 5 and 20 is still better than 10, so I will keep growing. But in practice, this often didn't make too much sense. The next thing we do is called the inverse document frequency. The inverse document frequency, the assumption is if you have a word that is very rare, it's important. If you have a word that is very common, it's not that important. So basically, we dampen the relevancy in very common words. And what that looks like is over all the documents that you have stored and all the tokens that you have extracted, this is the number of how many times does a token appear over all your documents, and this is the relevancy. So you can see here something that appears only like 50 times or so is very relevant, whereas something that appears many times, like 1,000, has very little relevancy at some point anymore, because it's just everywhere, so you find it in so many places. And the final thing that is kind of intuitive is the so-called field length norm. And we assume the shorter the text is where you find your token, the more relevant it is. So here, basically, we take the number of terms we have, 1 divided by the square root of that. And that's kind of intuitive. If you have like a blog post and you have the subject with very few tokens, and your hit is there, that's more relevant than in the very long body where you have hundreds of thousands of tokens. If you have your hit there, it's not that relevant anymore. And you can actually try that out or have Elasticsearch explain why something has a specific relevancy. And here you can see, for example, we are searching for father, and we want to actually have this explanation, why was something ranked in a specific way. And that explain true would then show you all the parts that we have discussed and what it calculated for those. So you see here that father, here the synonyms are at work. You can see the document frequency, the inverse document frequency, the query norm, etc. All the parts and what their value was, and then you could figure out why something was ranked higher than something else. So for example, if I search for father, these are the results that I'm getting back. I am your father, and Obi-Wan never told you what happened to your father. Why is the first one more relevant than the second one? Yes, it's shorter. That's the only difference, because the term frequency is the same. Both contain father once. The inverse document frequency is the same because we're searching for father across everything. The only thing that is slightly different is the length of the text. But as you can see here, the difference is relatively minor. It's 0.02 or something like that. So it doesn't really make much difference here. Okay, all of this was just true if you searched for a single term. If you search for multiple terms, it gets a bit more interesting. So let's assume we search for your father. And obviously the best match would contain both your and father. But the general idea is then like, what is more relevant? The documents just containing your or just father? And for that, you can actually draw that out. So this is a bit made up because it might be a bit difficult in the background, but the general idea is this. We assume that your is very common in Star Wars, so it doesn't have that much of a weight. Whereas father is very rare, so it's much more relevant. Also in the topic of Star Wars, the movie, like your probably appears hundreds of times, whereas father only very few times, but is very relevant there. So that's why it's much more relevant. The perfect document would contain your and father, so it would be this vector here. And then the question is, which documents are more relevant? The ones only containing father or only your? And then you basically draw out those vectors and then you calculate the angle. And the shorter the angle, the more relevant something is. So the most relevant documents would contain your father, the next most relevant ones just father, and the least relevant ones just your. And you would calculate that based on this angle. What if you have 3 terms? Then it would be 3-dimensional. And if you have 5 terms, it would be 5-dimensional. But that's rather hard to draw out, so that's why we're sticking to 2 dimensions, but you get the general idea. You just calculate the angle, and that's what makes the difference from the vector. Then we also have something called the coordination factor, where we basically reward. If you search for 3 terms, and one document contains all 3 terms, we want to reward that document and punish the ones only containing 2 or even 1 terms a bit. So here we are not just adding up the scores of each single term, but we're also multiplying that by 1 divided by the number of terms we're looking for. And you see, if you have all 3 terms, it would be multiplied by 1, otherwise 2/3 or 1/3. And then you can put all of that together to the practical scoring function, which looks pretty complicated, but we have covered all the parts here. So you can see we have the term frequency, the inverse document frequency. You could boost something where you say a specific field or a specific token is more relevant than other ones. You have the coordination factor and this query norm. You put all of that together, and then you get the score. You could also write your own custom function score if you need that. So for example, you could say, if you have a newspaper, stuff that happened today or yesterday might be much more relevant than what happened a month ago. So you're not only searching for the tokens, but you would also have like something like time in the query, where you're basically decaying out, like radioactive decay, decaying out older articles. Or if you have a geo search for like restaurants nearby, you would search, for example, you're looking for pizza, but then you would decay out like pizza that is further away might be less relevant than what is closer. So you could change that function score. The simplest example you could have is, just to quickly show that, is a random score which randomly scores the document. So when I run that, you can see, no, I am your father has 0.5 and is the first one. And when you run that many times, it will just jump around because the random score will be random, like what you expect. Why might this be relevant? For what could this be useful? Yes, if you want to have a random sample of data from a very large text body, that is something that makes sense. The other thing, if you're at a conference and they have like a giveaway, a prize, like you enter your details and somebody needs to win that, you could run the query with Elasticsearch with a random score. Because then we basically would run your names through random score with a size of 1 and get 1 lucky winner back. That's how I would do a raffle with Elasticsearch. Okay. Something else, people sometimes want to do that. I want to compare scores, 100% perfect versus a 50% match. Like I want to assign the score percentages. And the documentation is relatively clear about that. Like they have their own page, the scores as percentages, which starts with don't do this, because it really doesn't work. Let me show you why. So let's assume we have, these are my father's machines. What remains if I store, these are my father's machines? My father machine, I think. It should be my father. You can see synonym would work. My father, dad, machine. These are the 3 tokens that remain. So we're storing that. We're storing that in a document 4. And then we're searching for my father machine. And you would assume that this is the perfect match, right? Because it has all the 3 tokens that remain from this text. And then you could say, this has 2.92 something, the score. So this might be 100%. And this is then some other percentage of that. So you would say 2.9, that's the 100% match. Okay? So far so good? Nobody disagrees? The problem is what happens if we delete that document and run the same query again. Then suddenly the highest score that you would have is 1.2. And then is a question like, is this now a 43% match? Or is this the new 100% match? And the next problem is, this is maybe a bit made up, but let's assume we get another document where we have these droids are my father's machines. And you search for the same thing. What do you expect to happen? It will be a bit more relevant because of the term frequency, where if the document contains the term multiple times, it will be more relevant. And we have father twice, and we have droid machine, so that's there twice as well. And if you search for that, you have suddenly a 3-point-something score. Suddenly you have a 103% score. That's why trying to calculate or compare scores between queries or making them or turning them into percentages doesn't work. A score is only relevant within one query and is not comparable to any other queries. And don't try to turn it into percentages. This is not helpful. This is just not working. You just shouldn't do that. Okay, so since we're running a bit low on time, something that people always ask is like performance. Like, why is this super fast? Like, show us why this performs better than other systems. And my favorite comic about this question is this one. And this is what is happening at every benchmark that some vendor puts out about their software and their competitors. And basically, you always find some scenario where you kill your competition, and then you are much faster. And I remember that MongoDB, Cassandra, and Couchbase, like a few years ago, had that. Within a few months, all of them made a benchmark with the other ones, and each one of them managed to find some scenario where they were at least twice as fast as the others. And that's pretty much what you get from benchmarks from a vendor. You can benchmark yourself, but you will need to benchmark for your data, your queries, your read-write ratio, your hardware. You can benchmark for your specific scenario, and that makes sense. But don't believe in any benchmarks anybody else puts out, because those are normally not what you will have. Yeah. And then the other thing is, people often say like, oh, we have this huge use case. We have 1 million documents. And it's a bit like Dr. Evil coming back from the past and asking for ransom for $1 million, which nowadays is not that much anymore, and everybody laughs at it. And for us, that's pretty much the same for Elasticsearch. Like 1 million documents is normally not such a big use case. That's kind of like breakfast. That's nice and easy, and you can do that to warm up. So to wrap up, we've looked a bit into storing data and what we're doing in all these steps. We've looked at scoring and how scoring works, and that is really one of the things that doesn't happen at all in a database. A database is just black and white, yes and no, something is there or something is not there, but it doesn't give you the relevancy. Also, it does less work when storing data, but that doing more work up front will make your queries faster later on. Whereas if you do that like percentage search, that will be very slow because you didn't do the work up front, and then you need to repeat it for every single query. There would be other things we didn't really talk about today, so highlighting the results, Boolean queries, boosting specific fields or specific terms. We looked shortly into performance. Those are things that you could do. By the way, if all of that sounds super complicated, we also made or are in the process of making something we call App-Search, which is basically taking care of that, so you don't need to know all the details. It's like a wrapped package for that, and we have combined that. So what you have, for example, let's assume you have like a search, and you have a search box, and you can just search. You could do a geographic search where you say, okay, San Francisco, and then we would know, okay, if you store it in the background, this is what San Francisco would be. You would have pagination. You could have like numeric fields to filter for the price. You have filters where you say it has, I don't know, parking nearby, and then you have highlighting for the term. Here you search for burritos, and here we just find the burrito in the background. And it's basically just packaged. You have an API you interact with, but you don't need to know like the internals of how it works. But you can still build that because this is just built around Elasticsearch, like and kind of like wrapper around it, a nicer interface. You also would get an interface, for example, the right-hand side here, this would be your website, you search for sedan, and this is what the results that you get back, and this, for example, would be promoted. And you have a UI in the background where you can actually simulate a search, and then you could say, for this search term, I want to have a promoted result. And you could see this is what you would get back, and this also does like click tracking to know what people are clicking on, what works. It would log your queries to see what are people searching for. What results do they get? Do they click on anything? Do they need to go to the 5th page to find what they're looking for? To tweak that. So it's kind of like a bit more of a solution and not just an API to use. You could define synonyms and all that kind of stuff. With that, I think we have like 3 minutes or so for questions. Any questions? Also, I have a bunch of stickers over there. Just grab stickers if you want any afterwards. Questions? Did anybody post any questions? Oops. So, what scoring algorithm is behind finding matched sentences? You mean when you do a phrase search? So when we do a phrase search, basically there is that, yes or no? Because otherwise I will assume we are talking about phrase search. So phrase search will make sure all the terms you're looking for need to be there, they need to be in the right order. And then you would just run through the same parts of the relevancy that we have talked about. So we would take the score of every one that we have, and then you would, for example, have, if you search for one specific phrase, if that phrase appears twice in one document, it would be ranked higher. If the overall document is shorter than another document, the shorter one would be ranked higher, but it's kind of the same approach. It's just a combination of more steps, basically, but otherwise it's just doing the same thing. I hope that makes sense. Yes? Yes, so what you generally do is, search is normally not super large in terms of document size. What you would do is, you would store the sentences multiple ways. So you would have multiple analyzers for the same input field. So for example, our quote, we would store our quote once with stop words removed and once without stop words removed. So we just keep the stop words. And then what you do is basically you search over all these variations, and then you find what might be the most relevant. For example, if you then do, you would say that, you could say if that makes more sense for you if you do a phrase search and you want the entire phrase, just the lowercase one without stop words removed might be the most relevant one, and you could boost that up. So the general idea is you don't just store it once and then you have tough luck if you try to find it differently, but you store the document, or you analyze the text multiple times and store it, and then search across all of them to find the most relevant ones. Also, for example, maybe the Polish analyzer doesn't work perfectly for something. You might also store the text once with the Polish analyzer and once just lowercase without it. And then you just take the terms that you have. And if something matches exactly, that might be more relevant than what we stem down with the Polish analyzer. It will depend a bit on your use case. And you normally, what you need to define is, you need to say like, these are some example documents I have, these are some sample queries that I have, and this is the outcome that I expect. You will need to create that, but that is very domain specific, so there is no general solution for that. You will really need to create it for your use case and what your users are expecting to make your search work well. That's the general idea. Sure, 1 minute left.
Easy to integrate click data to improve the relevance of the documents.
So the click data is you would need a function score, and you would need to keep track like this has been clicked X times, but yes, if you have a function score, then you could just add that. Or for example, if you have like likes on Facebook or whatever, you could include those in the search results as well. But you would need a function score where you basically have the general score for the terms, and then like having like this decaying out of something like either geographically or time-wise, you could also mix in the likes or the clicks or whatever to boost something up that is like good quality, for example. Or if you have ratings, you might include those as well. It will require a function score because it's not like built in, and you need to figure out what makes sense if you add that or multiply it or whatever makes sense. We have some good blog posts about that actually, also for ratings, for example, where it's not, if you have 1 5-star rating, is that better than 5 5-star and 1 4-star rating? There are some algorithms where you need to tweak these algorithms and you need to find like the right balance for that, but you can totally do that with a custom function score, yes. Cool. I think we're out of time. Just come to me afterwards with a question. Thanks a lot.